We're going to continue Lesson 1.2, Mathematical Models and Catalog of Essential Functions. We have already looked at linear functions, polynomial functions, and power functions, and so now we're on to rational functions. A rational function is when you have a polynomial in the numerator and a polynomial in the denominator. So an example right here would be 1 over x. And so you're going to have some restrictions on your domain. And remember, the restrictions are from your denominator because you cannot divide by 0. So that brings things that it can't be. So for this one, your domain is going to be, I'm going to write this one in set notation, the set of x such that x cannot equal 0. And in interval notation, it would have been negative infinity to 0 or 0 to positive infinity. And to graph that, we graph it and it would look like this, where it jumps over. And that jumping over of the 0, remember it gets really, really close to it, never touches. Remember, that's called an asymptote. So let's look at this function. So this is a rational function as well. It's got a polynomial in the numerator, a polynomial in the denominator. And then we need to see what your domain is going to be. You can graph it and look at it and see. And so right here's your asymptote here, and your other asymptote over here. And so your domain is using set notation, x such that x does not equal a positive or negative 2. Now, that being said, we don't have to graph it to be able to see it. We can get it from right here. Of course, this is what this graph looks like. But taking the denominator, x squared minus 4, it cannot equal 0. This is a difference of squares. You can also solve it for x squared and take the square root, which I'm going to do. So I'm going to move the 4 over, and I'm going to take the square root of both sides. And I get x cannot equal positive or negative 2. And don't forget to close off the set notation. The next type of function we look at are algebraic functions. Now, algebraic functions are considered when it can be constructed using algebraic operations. And you're like, well, we just looked at things that were algebraic operations. Yeah, we did. So we have addition, subtraction, multiplication, division, taking roots. Those were polynomials, and that's fine. And all rational functions are algebraic functions. They're automatically, but there are more. Sometimes we don't define them with just the rational or a polynomial. So here's some that we can look at. So right here's f of x equals the square root of x squared plus 1. And then this one, that wouldn't fall nice and neatly into anything, any of the other ones that we've looked at. So this is an algebraic function. It's just multiplication, you got some subtraction, addition, we're taking some roots, and it's an algebraic function. It's just not a nice, neat one that we usually look at. And the graphs can look really different as well. So here's the graph of x, square root of x plus 3. And that doesn't look like anything you've seen, so that looks like a check mark to me. And then the next one is the fourth root of x squared minus 25. And that looks a little bit more neat. But then down here, this third one, it's x to the 2/3, x minus 2, squared. And that looks a little different than what you typically see. But it's an algebraic function. An example of an algebraic function that occurs naturally is the theory of relativity. This is the theory of relativity right here. And so it's the mass of a particle with velocity v is equal to this expression. Now, this is a theory. It's naturally occurring, but it's not a nice, neat polynomial. It's just an algebraic expression, an algebraic. So m0 is the rest mass of a particle, and c, it's a constant, it's the speed of light. And you would use this to figure out the velocity. The next family of functions we're looking at are the trigonometric functions. So your sine, your cosine, tangent, we're going to look at those. And you also have secant, cosecant, cotangent. And so the first one we're going to look at is sine. Now, if you're having a hard time remembering sine, just think about your unit circle and this point right here, and that is the point 1, 0. And sine is sine y, sine y. So it's the y value. So sine starts here at 0. And then as we go through, it takes one complete rotation to get back around. So the period is 2 pi. And so notice in calculus that we're going to use radians. We don't use degrees much. We'll tell you if we use degrees, but otherwise just we're using radians. So I'm going to write a pi here, a 2 pi there, and in the middle, which, you know, all this comes from is these 4 points around, pi over 2 and 3 pi over 2. That's 3. All right, so going through this, it starts at 0, and the amplitude, it goes up to 1, and it'll go down to -1. It doesn't go any higher or any lower than that if it's just the standard sine of x graph function. So at pi over 2, we're up at 1. And then at pi, we come back to 0, 3 pi over 2, and then 2 pi. So this is, it will continue the other way as well. I didn't mark those. So your domain on these, your domain is -infinity to +infinity, all real numbers. The range on this one, notice it has to do with the amplitude. It only goes up to 1, and actually includes 1, and it goes down to -1, includes it. Now your zeros, we haven't talked about that one yet. It's anywhere it crosses. So the zeros for sine, it's going to be at 0, and then also any time that x is equal to n pi, where n is an integer. See, it went through it at 1 pi, 2 pi, it'll go through it at 3 pi, and then last is the period, which we've talked about. The period occurs when it repeats itself. The period is 2 pi, which what that means is that the sine of x plus 2 pi, so if we go around once, it's just the same thing as sine of x. All right, let's look at it for cosine. It's not a whole lot different. It's just because now when we look at cosine, if we look over here at the unit circle I drew, it starts at 1. It's the x. So it's going to start up here at 1. It'll have the same amplitude. And then we have pi, 2 pi, pi over 2, 3 pi over 2. So drawing this one, starts up here at 1, goes through pi over 2, at pi it's down to -1, and so it would repeat itself on the back side because it is also continuous, it cycles. And so our domain, same thing, it's negative infinity to positive infinity. The range is the same thing, it's a bracket, -1 to +1. The zeros are different on this one. They occur here at pi over 2 and 3 pi over 2. So that's going to give us where x is equal to n pi over 2, where n equals odd integers. Okay, and it's only odd because no, it's 1, 3, the next one would be 5. And then the period, it's the same thing. It's 2 pi. And so, same thing about when you find the cosine of x plus 2 pi, it's going to be the same thing as if it were just the cosine of x. So because of that periodic nature of the functions, because when you loop around once it's equal to that same thing, it makes suitable for modeling repetitive phenomena such as tides, it repeats itself, vibrating springs repeat themselves, sound waves repeat themselves. Some really neat things that you can deal with in physics that can be modeled with the sines and cosine functions. The next trig function we're going to deal with is the tangent function, and it's related to the sine and the cosine. It's sine divided by cosine, and so we're going to look at it. If we graph it, sine, it's undefined anywhere that cosine was 0 at. So that was at pi over 2. And also at 3 pi over 2. So notice any where that the zeros of the cosine function were at. So we can go back this way as well. And it would be negative pi over 2. And then also negative 3 pi over 2. It will go through 0 anytime the sine was 0. So that was at all right here. So this is 0, this is pi. Over here, if we did it again, this would be 2 pi. Negative pi. And then we draw them. They go up like this. So that's the graph. Now your domain on this one is not quite the same. So your domain is x such that x cannot equal positive or negative pi. So positive or negative pi over 3. So this would be x cannot equal n pi over 2, where n is an element of odd integers. That's your domain. Then your range, this one's actually different than the other ones because it can actually go all the way down to negative infinity and all the way up to positive infinity. And then the period on this one, how often it repeats itself, it's going to be pi. So this distance was pi. So instead of it being 2 pi like sine and cosine, it's just a single pi, 1 pi. The last three trig functions that we look at are cosecant, secant, and cotangent. And they are the reciprocal functions. So remember, cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. In order to graph these, you've got to know the original function. So remember that sine started at 0 and it went through this cycle, one period. And that was at pi. This is at 2 pi. And so I'm going to draw this cosecant function here in blue because what happens is that they come and they go the opposite way. So this one has asymptotes. That's the wrong place. Right here at 0, at pi, at negative pi. And that's your cosecant function. So I'm going to erase the sine function here. And just keep my cosecant function. Secant is the reciprocal of cosine. And it started up here at 1 and cycled this way. So this was pi over 2, and this was 3 pi over 2. And so secant is the reciprocal of cosine, so it graphs. And it has asymptotes as well, but I'm going to go ahead and erase cosine function off. And then the asymptotes are right here. And the last one is the tangent function, or the cotangent function. I'm not going to draw the tangent function on this one because it would get way too confusing. So this one flips it and moves it over. So it's going to look like this. And so this would be pi. The next function type is an exponential function. And so it happens that it can be a growth, and that would be when a is greater than 1. Or if it's a decay, and that would be when a is between 0 and 1. So the domain, well, let's graph it and I'll show you. So the growth looks like this. It's going to go through 1 right here. Then your domain is negative infinity to positive infinity. Your range is going to be, looking at that, what do you think? Well, it looks like it goes down to 0 and never touches it and then goes up to positive infinity. And that would be right. And then the next one over here was a decay, and it goes down. And it also goes through 1. But it's a decay, so it's decreasing. And your domain on it is still negative infinity to positive infinity, and the range is still 0 to positive infinity. And exponential functions are very useful for modeling natural phenomenon. such as population growth, radioactive decay. And notice growth has to be, again, greater than 1, and decay is actually less than 1, but it's positive. If it were negative, it would flip it over, which we'll talk about in the next lesson. The next family of functions was the logarithmic function, and this is right here, where base A, it's a positive constant, and logarithmic functions are the inverses of exponentials. So logarithm and exponentials are inverses of each other. And as you can see, looking at the graph over here on the right, are the different bases. So the yellow one's a base 2, the blue one is a base 5. No, that was a base 3, sorry. And then the pink one is a base 5, and then the black one's a base 10. Notice as the base gets larger, what happens to the graph? It's getting shallower, so things happen more quickly on it as the base gets larger. So your domain for these is from 0 to positive infinity. They don't actually ever hit 0, so make sure it's a parenthesis there. And then your range is negative infinity to positive infinity. So the graphs that we looked at are transcendental functions, and it's those that are not algebraic. So transcendental functions are functions that are not algebraic, so no polynomial, stuff like that. So the ones that we just looked at include trigonometric, your inverse trigonometric, exponential, logarithmic function, and many others that have never been named, just like the algebraic. The ones that we knew were included, but there were a bunch of other ones as well. So I want you to look at these 4 functions. And I want you to tell me what type of functions they are. So A, B, C, and D. I want you to answer it in the question at the end of this video.